Okay, so this is the example we were working on in class last Wednesday. In chapter 5, the previous sections, you learned about integration techniques for the for finding antiderivatives, for finding integrals. And now in section 5.9, we deal with integrals that you cannot find the antiderivative of. So like the integral of e to the 1 over x dx from 1 to 2, you cannot get that antiderivative. Okay, and so let's see here. So what did we do last time? Hold that thought, Mohammed. Hold that thought. We talked about the different rules, different approximation rules for, oh, no problem, no problem. So we learned that we can, well, if I bring up the ebook, like, give me just a moment here to bring up that ebook. One moment. Bring up the ebook, section 5.9. One moment here. Yeah, so we talked in the last class about how we can approximate integrals using some different rules. And of course, we looked at figure 1, and we saw that, well, we could define the heights of rectangles over an interval using left endpoints of each subinterval. That's figure 1a. Figure 1b, we could define the heights of rectangles using the right endpoints of each subinterval. So the function values of the right endpoints would be the heights of the rectangles for the different subintervals. And then, of course, we talked about the midpoint rule, where you, for the different subintervals, you take midpoints and evaluate the function at the midpoints, and then those will determine the heights of the subrectangles, or of the rectangles, I should say. And that was good. And then we even mentioned that there's a trapezoidal rule approximation where we can, along each subinterval, create a trapezoid, and that's a nice way to approximate the area under a curve. And then there's even a rule called Simpson's rule. Okay, and this is all what we talked about last time. Simpson's rule is where you, for each subinterval, you have 3 equally spaced points, and you pass a parabola through the function values of those 3 equally spaced points, and that creates a really a nice approximation, because parabolas can approximate curves usually better than line segments. So all of these techniques have formulas associated with them, and we had, let me just bring this up. We had a handout that I made for numerical integration formulas. So, for instance, you have the trapezoidal rule, the midpoint rule. Okay, you have the corresponding formulas. Simpson's rule, there's a corresponding formula for that. And then for every one of these rules that approximate the true value of an integral, we have error-bound formulas as well. So we last time talked about applying the midpoint rule, okay, to approximate our integral. And once again, the integral is here. And we want to use m sub 10, which means use the midpoint rule and take the interval from 1 to 2. That's your bottom limit and your top limit for your integral. Take that interval from 1 to 2 and break it up into 10 subintervals. And that's what we did. That's what we did here. We broke that interval from 1 to 2 up into 10 subintervals. And then so each subinterval would be 1/10 long, because delta x is 2 minus 1 divided by 10. 10 is your number of subintervals, so that equals 1/10. And then every subinterval, the midpoint is halfway between. So x1 bar is 1.05, x2 bar is 1.15, x3 bar here is 1.25, and so on and so on. And you get all these midpoints, and you're going to use the formula for the midpoint formula. Take the delta x and multiply it by the sums of the function values evaluated at the midpoints. And then you add up all of your function values. And so, you evaluate each function value and add up all the function values and multiply by 0.10, and you'll get 2.019101885. Okay, so I'll answer questions at the end of class regarding the exam. Don't worry about that. We'll devote some time. Don't worry about that. So this here is an approximation, 2.019101885. That's an approximation to the true value of the integral. Okay, but the question is, how good of approximation is it? We used 10 subintervals. We got an estimate. Okay, and that's an estimate for our integral, but how good is it? Well, this is where now we continue the problem. So the next step is to estimate the error in our approximation. Estimate the error in our approximation. So to estimate the error in this midpoint rule approximation with 10 subintervals, what we have to do is we have to go now to our error-bound formulas. Okay, and you can see them here. So the left endpoint rule approximation, and I'm sorry, the left endpoint approximation and right endpoint approximation don't have corresponding error-bound formulas, but the midpoint rule does, trapezoidal rule does, and Simpson rule does. And so, of course, we're interested in the error bound for the midpoint rule. And bound on so what this is saying is that the bound on the error using the midpoint rule is less than or equal to K, big K, times the length of B minus A, that quantity cubed, over 24n squared. So in this formula, the B is known. That's the top limit of the integral. A is the bottom limit of the integral. And n is your number of subintervals. So everything's known except this value of k. This value of k we have to find. Now, according to the rule here, k is greater than or equal to the absolute value of the second derivative. K is greater than or equal to the absolute value of the second derivative. And this formula, if you take a course in numerical analysis like I did, actually in graduate school, they prove these formulas. For now, you're just going to apply them. So, okay, what's the goal? The goal is we want to estimate the error in our approximation. So again, we know that M10 is an approximation to this integral, and we want to know Okay, the error, which is, it's an error, our approximation has an error. It's the difference between the approximation M10 and the true value of the integral. And we would like to know, we would like to get an idea of how big this error is. So we're going to apply the error-bound formula here. And let's go forward into the solution. So, you know, here was our approximation. There's our M10. Now we continue the problem. So the estimate for the error of our approximation is given by this formula where I filled in some values. Let me give you a moment to copy up to here. All right, and then we'll continue. Let's see, Jonathan, the formula that like this formula here, I'm rewriting that on the current page. I'm rewriting that formula. So don't worry about that. I've rewritten it here. So the error bound for the midpoint rule approximation, the bound on the error, and we take the absolute value, but we care about the magnitude of the error. That's less than or equal to this big K value times, okay, well now what's 2? Well, 2 is equal to B. 1 is equal to A. And N is equal to 10. Because remember, we're using midpoint rule with 10 subintervals. So the error bound is equal to big K times the quantity 2 minus 1 cubed divided by 24 times n squared. Now big K is greater than or equal to the absolute value of the second derivative over our interval from 1 to 2. So in order to find K, I have to find the second derivative for our function. Okay, well recall that again the integral was from 1 to 2 of e to the 1 over x dx. So the e to the 1 over x power is my function value. Okay, and there it is. And now I'm going to find the first derivative. So of course, the e to the power of x to the negative first, we're going to use the chain rule to differentiate that. And the exponential function is the outer function. So the derivative of e to the x is e to the x. So using the chain rule, we get e to the power x to the negative first. And then we have to take the derivative of x to the negative first, which is just negative x to the negative second. And this will give us negative x to the negative second power times e to the power x to the negative first. That's our first derivative. Okay, are there any questions so far? Okay, well, let's proceed on then. Now we want the second derivative. So the second derivative is just the derivative of the first derivative. So here was the first derivative. And this negative sign, if you don't mind, I will factor that out in front. And so we have the derivative of a product x to the negative second times e to the power x to the negative first. So I'm going to use the product rule, which you know very well, along with the chain rule, to get my second derivative. Which will be 2 times x to the negative third times e to the power x to the negative first, plus x to the negative fourth times e to the power x to the negative first. Now, what we want to do with this second derivative is we want to find out where the second derivative, or I should say the absolute value of the second derivative, we want to find out where it's maximized over our interval from 1 to 2. So to help me do that, I want to rewrite the second derivative in a prettier form. So these negative exponents, well, first of all, what I do is the e to the power x to the negative first. I factor that out. And so I'll get e to the power x to the negative first times the quantity 2x to the negative third plus x to the negative fourth. But then 2 times x to the negative third, that's just 2 over x cubed. And x to the negative fourth is just 1 over x to the fourth. And now I have two fractions that I'm going to add together. So the goal is just to get this second derivative in a nice form, okay, in a nice form that I can analyze. So I have this 2 over x cubed, and what I'm going to do is multiply it on the top and the bottom by x, and then I have the plus 1 over x to the fourth. And this, then, I'll have a common denominator of x to the fourth. That gets me this fraction here. Well, that gets me the sum of those two fractions, but they have the common denominator. And finally, then, I can write the second derivative as you see here. Okay, take a moment. Okay, so question. Mohammed, the reason we need to get the second derivative is because if we look at our formula sheet here, and if you go to the in course content under chapter 5 in Blackboard, the course content link, you can download this under section 5.9. So this is the formula right here, and the value of k is there, and the criteria says that the value of k, to find it, be sure it's greater than or equal than the absolute value of the second derivative of your function. So that's why we're going after the second derivative, because we can't find that value of k until we find the second derivative. All right, Mohammed, does that make good sense? K is not the error. The error is the absolute value of E sub m, which is the error due to using the midpoint rule. But what we're doing is we don't know what that error is because we don't know the true value of the integral. But we can at least get a bound on the error. Notice it says here, notice it says that the error is less than or equal to this quantity here. So if we can find what that quantity is, it'll give us an idea on what our error is. All right, so now we want to find k. We have our second derivative. Okay, we have our second derivative. And so now let's go to the next page here. There's our second derivative. But remember, we want the absolute value. We want the absolute value of the second derivative. So when x is between 1 and 2, and that interval is what we care about, because those are that's the, our integral goes from 1 to 2. The e to the 1 over x is positive from when x is between 1 and 2, and 2x plus 1 over x to the fourth is positive when x is between 1 and 2. So the absolute value of the second derivative is simply equal to the second derivative. And that is a decreasing function when x is between 1 and 2. If you were to graph this function, you would see that it's a decreasing function. Now, what are we going to do with that? How's that going to help us? That second derivative decreases with x. So how's this going to help us? Well, let me show you here. So, if we just think about drawing a function, but in this case, I'll draw a decreasing function, and I'll call it the absolute value of the second derivative of x. It's just a picture, but it's our second derivative is decreasing, and so this is just a decreasing second derivative. Here's 1, and here's 2. X equals 1, x equals 2. Sorry, it's not drawn exactly to scale. And then here are values of the second derivative at x equals 1 and x equals 2. So where is that second derivative maximized? Is it maximized at x equals 1, based on the picture, or at x equals 2? What would you say? That's right, Jonathan, at x equals 1, because that value is larger. It's the largest value of the second derivative. And so that means then that the second derivative is maximized at x equals 1, or the absolute value of the second derivative is maximized at x equals 1. And so what I'm going to do to determine k is I'm gonna put in 1 for x on my second derivative and evaluate it. Okay, so here's me evaluating my second derivative when x equals 1, and I'm going to get 3e. K has to be greater than or equal then to 3 times e. So we want k to be, we want our error bound to be as informative as possible, so let k equal 3 times e. Okay, and so now we're able to get an idea of what the error is, or a bound on the error. Let you copy down to here. All right, And I want to make sure I'm pacing myself well. Please let me know if you have any questions. Yes, Susanna.
Yes, sorry, can you explain again how you knew it was a decreasing function?
Well, so of course, what you would do, I mean, the way you can think about it is e to the 1 over x power. The 1 over x power, okay, that's going to be decreasing with x. So e to the 1 over x power decreases. But also 2x plus 1 over x to the 4th power, that is also a decreasing function. It's not
Okay.
necessarily obvious, but if you were to graph that second derivative, you would see it's a strictly decreasing function. That's really the best way to do it.
Okay. Okay. Thank you.
And for your problems in WebAssign, and then section 5.9 is not on the exam, not on the first exam. But for the problems in WebAssign, the finding that k value, a lot of times you're going to have derivatives, second derivatives that are either decreasing or increasing, or there's an easy way to find k. And so, we're going to keep things pretty simple. Well, so now what I do is, okay, so I'm going to put in, one moment here. Okay, so I'm going to put in my value of k here. And then again, this is b, 2 is equal to b, a is equal to 1, n is equal to 10, and we're going to end up getting e over 800, which reduces to 0.0003398. So the error in approximating the integral using a midpoint rule with 10 subintervals, that approximation that we found, which was 2.019101885, that approximation is within about 3/10,000ths, of the true value. In other words, we're off by no more than about 3/10,000ths, or 0.0003398. So the question is, are you happy with that? Is that good enough, for your application? If you're doing like an astronomical, like if doing a calculation dealing with astronomy, that might be too big. That allowable, I want to be careful, that possible error. I mean, again, the error might be smaller, could be much smaller, for instance, than 0.0003398. But we have to at least allow that the error could be that large. And if you're doing very crucial computations where you have to be exact, maybe the midpoint rule with 10 subintervals isn't enough. What could you do to get a better approximation? What could you do with the midpoint rule to improve it? That's right, Yonatan. Use more rectangles, take more subintervals. That's exactly right. Okay, and we'll look at a problem. I mean, we're actually going to do another problem related to this problem. But first things first. Are there any questions? All right. Well, so I want to go back to the example. Is everybody good with this page?
Yes.
Okay, Clea, good. All right, well, let me go back to the example here. So this example really has three parts to it. We found a midpoint rule approximation. Now we have an estimate on the error of our approximation. The third question asks, okay, well, is this approximation an underestimate or an overestimate? Okay, so I mean, either the approximation would have to be an underestimate or an overestimate. So how are we going to determine that? Okay, well, here is the key to determining that. We learned, well, I want to be, yeah, we want to look at our function f of x equals e to the 1 over x. So again, our original integral is from 1 to 2 of the power e to the 1 over x dx. Okay, so there's our function. And the e to the 1 over x is a concave up function. Okay, that is a concave up function. Now, how do we know that? Well, when we found the second derivative here, what can you tell me about this second derivative? Over the interval from 1 to 2, the second derivative is always greater than 0, right? It's always greater than 0. That means then that our function f of x, if the second derivative is positive over our interval from 1 to 2, that means then that our function is concave up. How many recall that from calculus 1? If the second derivative of the function is positive, your function is concave up.
Yeah, we do.
Okay, good, good. Clea remembers that, and well, okay. So look at what I've done here. I've just drawn a picture of a concave up function. Okay. Yeah. Question, Mohammed?
Yeah, if we were saying like the second derivative was concave up, would it just be if it was positive or negative, or would we have to like actually plug in values and check between the range?
Well, the second derivative is positive for our values of x between 1 and 2. There's no question that the second derivative is positive. And so that means our function is concave up. You do have to like look at the values you're working with, of course, and but you know, definitely our function's concave up. I mean, you could graph the function too, and you would see that you have a function that looks like what I've drawn here, and it is concave up. But of course, you know, yes, Claire.
When it's concave up, in this case we said it's underestimate, but like, is this always true? Like,
Well,
it's
yeah,
concave
let's
up.
talk about that. Good question. Why would it be an underestimate? So what I'm doing here in the picture is, okay, I have a interval. So think about how we do the midpoint rule. So I just have like some subinterval here. Okay, subinterval, and this here is our midpoint. We use the midpoint to determine the height of the rectangle. Okay, and when we add up the rectangles using the midpoint rule, how do the rectangles, how does the area that the rectangles give us, how does it relate to the area that we're looking for? Well, you can see here that the area here did not capture this area here. So that's what I call lost area. That's area that we wanted because it's underneath the curve. Okay, again, we're trying to approximate a definite integral. That would be the area underneath the curve. So that's lost area. Okay, we didn't capture that area. But then over here, we gained some area. We gained some area right here, that green area. Okay, now that area is not area under the curve, but it's area that nevertheless we've gained. So the question is, how does the lost area compare with the gained area? If you take the lost area, I mean, based on the picture, if you take the lost area, let me do it below here. If you take the lost area in red there and subtract the gained area, is the area positive or negative? What do you think? Is the lost area more than the gained area or less? The lost area is more. It's more than the gained area. This lost area here, by virtue of the fact that we have a concave up function, that lost area is more than the area we gained. So in other words, we are, I want to say this the right way, we are underestimating our integral. The midpoint rule with the concave up function is going to give us an underestimate. Okay, because the lost area that the midpoint rule doesn't capture is more than the gained area that the midpoint rule does capture. But in the net total, we're not gonna, the midpoint rule is gonna underestimate the midpoint rule approximation will underestimate the true value of the integral. Okay. Now, what if you had a concave down function? If you had a concave down function, would the midpoint rule be an overestimate or an underestimate? Then that's right, Jonathan, you'll gain more than you lose. You'll gain more than you lose. Okay, so in other words, this is just an aside here, but let's say that you have a nope, I want to have that. You have to think about this a little bit because there are going to be problems like this in WebAssign for section 5.9, and some of them are multiple choice. You have to be very careful. Whoops, hold on. Okay, so there's a concave down function, and what I can do is I can have a subinterval, and then here's the midpoint right here. Midpoint determines the height of that rectangle. Okay. And here, I want to be a little bit careful now. One moment. One moment. So, one moment, class. One moment. Let me just put this here. Not working too well here. Hold on. Okay, so just give me a moment here. Yeah. So this area here is the, I mean, it's a little bit, this is the lost area. And by the way, our function f is concave down. I see what I'm doing wrong here. I'm not doing anything wrong, but my, this should be a little bit, you know, a little bit, you know, a little bit more there. Yeah. Okay. And then I want to be careful what color I use. This area here it's not perfect, but this here is gained area, right? That's area that the midpoint rule includes. And then the yellow area is area that we want, but the midpoint rule doesn't capture that area. In this case, for a concave down function, the gained area, how does the gained area compare to the lost area? Is the gained area more or less? Is the gained area greater than the lost area? Or is the gained area less than the lost area? It's more. That's right, Jonathan. And so this means then that the midpoint rule, since the gained area is more than the lost area, the midpoint rule, doesn't matter how many subintervals you use, it will overestimate. It will overestimate your integral. It will overestimate it. Okay, so a lot of times these questions in WebAssign, that is the approximation an underestimate or an overestimate, that sort of thing. A lot of times it just boils down to looking at the concavity of the function, maybe drawing a little picture to help you come up with a reasonable answer. It's really, you know, but it's important. It's important. Okay, are there any questions on that? All right, I'll stop the recording then.